Welcome back to our heat transfer class, where we're delving deeper into the one-dimensional, steady-state heat conduction. This video was made with the support of Energy. The topic of one-dimensional steady-state conduction is divided in several lessons. There is at least one video for each lesson. Let's continue with the fifth one. The lesson about internal heat generation is divided into several parts. Let's start analyzing the diffusion equation for conduction heat transfer with internal heat generation. A common thermal energy generation process involves the conversion from electrical to thermal energy in a current-carrying medium. Energy generation may also occur because of the deceleration and absorption of neutrons in the fuel element of a nuclear reactor or exothermic chemical reactions occurring within a medium. Conversion from electromagnetic to thermal energy may occur due to the absorption of radiation within the medium. As seen in Topic 1, the heat diffusion equation is an energy balance per unit of volume inside a solid to which we have applied Fourier's law to evaluate conduction fluxes. Solving this differential equation in partial derivatives, we find the temperature field. Knowing the temperature field and applying Fourier's law, we can calculate the heat flux at any point in the solid. For one-dimensional steady-state conduction, this equation is simplified and can be solved. We will call G to the volumetric internal heat generation in watts per cubic meter. We will consider solids where the thermal conductivity is uniform and does not change with temperature. The heat generated inside is considered to be uniformly distributed. Internal heat generation in a plane wall. In a plane wall, the diffusion equation can be written as the second derivative of temperature equals G divided by lambda with a negative sign. Integrating once and once again, we obtain the temperature distribution that is a second-order polynomial. C2 is the value of the temperature in the origin of coordinates. C1 is the value of the derivative in the origin of coordinates. To find them, we must apply two boundary conditions. Internal heat generation in a cylinder or a cylindrical wall. Like for plane walls, for cylindrical walls, we must integrate the diffusion equation twice. To find C1 and C2, we must apply two boundary conditions. Internal heat generation in a sphere or a spherical wall. For spherical coordinates, the process is the same. After analyzing the diffusion equation in three different coordinates, we can compare them. Now, it is time to apply these results to solve exercises of internal heat generation. Examples. A disc-shaped electronic chip is installed horizontally on an insulating medium. In steady state, the chip consumes an electrical power, PE of 10 watts. Using the data given in the table, calculate the surface temperature, T1, and the maximum temperature, T0. Stop the video here and try to solve this exercise. The first step is to calculate the surface temperature, T1. Because all the electrical power is converted into heat and transferred by convection to the surrounding air. Applying the Newton's law for convection, you can obtain the surface temperature. Assuming an uniform internal heat generation, we can obtain the volumetric heat generation, G. Now, is time to use the results of the integration of the diffusion equation. The first boundary condition is a result of the insulation of the chip. The heat flux is 0 for x equal to 0. Therefore, the temperature derivative is 0 and also the constant C1. The second boundary condition is that the temperature for x equal to the thickness T is T1. Applying this condition, we can calculate the constant C2. which is the temperature for x equal to 0. In this case, the maximum temperature of the chip. Let's analyze now a cylindrical wall. This tube is insulated in its outer surface. Inside, there is a fluid circulating at a low temperature. The tube wall has an uniform internal heat generation. With the data given in the table, find the temperature distribution and the maximum temperature of the tube. Stop the video here and try to solve this exercise. The first step in this kind of exercises is to find the temperature of the surface where heat is released. In this case, to the fluid circulating through the tube. First, we calculate the energy generated in the tube wall per unit time. Because the tube is insulated, all the energy generated is sent to the fluid in the steady state. We apply the Newton's law for convection in the inner surface. Therefore, thanks to the energy balance in the inner surface, we can find the inner surface temperature. Now, we can use the results of the cylindrical wall for the temperature distribution and the derivative of T. Applying the boundary condition for the insulated surface, where the heat flux is 0 and the derivative of T is 0, we can find the expression for C1. Applying the boundary condition for Ri, where the temperature is T1, we can find C2. We can substitute this value in the T equation and arrange the terms on it. With this expression, we can calculate the temperature of R equal to Ro. We can also draw the temperature distribution, where the slope for the outer diameter is 0. Finally, we will analyze the sphere. This is a sphere with uniform internal heat generation. The heat generated is dissipated by convection in the surface. With the data in the table, calculate the surface temperature, the maximum temperature and the temperature distribution. Stop the video here and try to solve the exercise. The heat generated in the sphere per unit time is the volumetric heat generation multiplied by the volume. Before applying the Newton's law, we need to calculate the external area. The heat balance applied in the sphere surface gives us the value of the surface temperature. This is one of the boundary conditions when applying the diffusion equation. Now, we can use the results of the integration of the diffusion equation in spherical coordinates. To find a second boundary condition, we must think on the symmetry of the temperature distribution when the boundary conditions are symmetrical. Because the symmetry, the derivative of T for R equal to 0 is 0. The integration constant C1 is 0. For finding C2, we must apply the boundary condition in the sphere surface where we know the temperature. Using this expression, we can find the temperature distribution equation. Terms can be rearranged. The maximum temperature corresponds to the center of the sphere. With this equation for the temperature profile, we can calculate the curve of T as functions of the radius.